Welcome to Brain Vision.
For this question, we're asked to look at figure 36, where two parallel wires are placed in the plane. One of the wires carries a current, which I call I1 of 25 amperes, and the distance from the nearest wire, center to center, is R, and it's R1, and it's 2.8 millimeters, or 2.8 times 10 to the minus 3 meters. You can tell that R2 then is double R1. It's two of R1s, and the current I2 is 28 amperes from the figure there. So what we're trying to figure out is the force per unit length each wire exerts on the other two wires. So to do that, we're going to first figure out the force from one of the wires. We'll call this F1. So the equation here from magnetic field force is mu naught, which is 4 pi times 10 to the minus 7 newtons per ampere squared. It's the magnetic permeability of free space. You can look up that constant if you want to know more. So it's mu naught times I1 times I2 divided by 2 pi. The distance here is r sub 1. So we plug those values into this expression. We find that this is equal to 0.05. The units here would be newtons per meter if we want to know the force per unit length per 1 meter. So 0.05 newtons divided by 1 meter is 0.05 newtons per meter. Okay, so then F2 here is going to be equal to mu naught, it's the same mu naught as above, times I1 times I2, but this time the distance is R2, so this is divided by 2 times pi times R2. But we said R2 was 2 times R1, so it's going to be the exact same value as the force above, F1, except this time it's going to be cut in half. It's going to be divided by 2 because R2 is 2 times R1. So we plug 2R1 in for R2. We get the same expression as above, except with this extra 2 term. So it's F1 over 2. So we find that this is equal to 0.025 newtons, and you divide it by 1 meter, it's 0.025 newtons per meter. We can box that in as our solution to the second part of the question.